Alright guys, in this video we're going to talk about the structure of the atom and the subatomic particles that are in the atom. And then we briefly touch base about the periodic table and its sections. There are actually three subatomic particles that are inside of the atom. We got the electrons, the protons, and the neutrons. So you want to make sure you know their locations and you know what the charge is going to be. And you want to have a rough idea of their masses. Like you don't necessarily have to know or memorize the charges or the masses of these subatomic particles, but you want to make sure you know who is heavier than the other. So to start out with, an atom contains a very small center. It's going to be called a nucleus, and the nucleus has two subatomic particles. We got the neutrons and we got the protons inside the nucleus. The symbol for the neutrons is N, the symbol for protons is P. The neutrons are actually electrically neutral, so there's no charge on it. However, the protons have a positive charge on it. So I can say the protons, or actually I can say the nucleus overall is a positively charged. Then around the nucleus we have these well-defined energy shells. These well-defined energy shells actually represents the periods in the periodic table. So I'll talk about the periods of the periodic table in a little bit. Okay, so these well-defined energy shells contains the electrons, like for example this first one, so I can call this one first energy shell, this is going to be the second energy shell, and this is the third energy shell. So now you don't necessarily have to have only three energy shells. It really depends on the type of element you're talking about. You could have only maybe one energy shell, or maybe two energy shell, or even maybe more than three. So in the first energy shell you have two electrons, and then in the second energy shell you have a total of 8 electrons, and then it goes on and on. So now how many electrons you will have in a particular energy shell, that really depends on which particular energy shell you're talking about, and that's something you guys learn when you talk about quantum mechanics. But for right now, just know that these are these energy shells contains the electrons. All right, so this is going to be the electrons in there. The symbol for the electrons is going to be just E, and they are actually negatively charged. So in a neutral atom, the number of electrons are actually going to be equal to the number of protons. So that way there is no excessive positive charge or the negative charge. Because remember, protons being positive and electrons being negative, both of those charges are being balanced by one another, so you don't have a positive charge or a negative charge overall on an atom. Anytime they are not the same, that's when you get in charge. So you could make a positively charged ion or a negatively charged ion, and we'll talk about that in a little bit. Now, other things I want to kind of mention a little bit about the masses of these neutrons, protons, and electrons. So you don't necessarily have to know you don't have to memorize what the exact mass of these protons and neutrons are, but know roughly the mass of the protons and neutrons is the same. However, the electrons are a lot less massive, so they are going to be less massive than the protons. Okay, so then let's focus on what really determines which particular element we're talking about, and it turns out it's actually the number of protons that tells you which particular element you're talking about. And there is another terminology that's represented by the protons. The protons is also going to be equal to the atomic number. So it's a very common term when they say what's the atomic number of an element, what they're really referring to, how many protons you have inside the nucleus. So you don't really change the number of protons of an element that easily. Anytime you change the number of protons in an element, you are actually changing the element as well. Okay. In a chemical reaction, you never change the number of protons. The number of protons only changes in nuclear reactions, but for the most part, here we're going to be talking about chemical reactions. Like I said, there wasn't a relation between the protons and electrons. There is really not a direct relation between the protons and neutrons. However, related by the number of protons and the neutrons. Another way of saying the number of protons plus the number of neutrons actually tells you what the mass number is going to be. And we don't really include the electrons in there. That's because we said earlier the electrons are less massive than the protons. So most of the mass of the element does come from the protons and neutrons in there. Okay, moving along, we want to make sure you know what the valence shell and electrons are. The valence shell is going to be the outermost shell. The outermost shell in this particular example is the third one, okay? And then, however, electrons, so I'll say it's the third one here, and however many electrons you have is going to be the valence electrons. So the electrons in the outermost shell will be the valence electrons. And in this particular case, if I go back, there's only one valence electrons in this third shell, so I can go and write down there is one valence electrons in there. And believe it or not, in chemical reactions, you will have only the valence electrons that will play in a role. The core electrons that's going to be inside the valence shells or does not play any role in the chemical reactions at all. So the core electrons or the core shells are going to be the shells between the nucleus and the valence shell. So make sure you know the terminologies of all these. Okay, so then where is most of the mass of the atom is actually coming from? It's coming from the nucleus. Remember what we said about the electrons? Electrons are about 1,000 times less massive than the protons. So most of the mass has to be coming from the nucleus in that case. However, the size of the atom comes from the shells, like whichever particular shell or the outermost shell is, that gives you the relative size of the atom. The nucleus is actually very, very small compared to the overall size of the atom. Okay, let's talk about the periodic table. In a periodic table, we have 4 sections, okay? So I got this section right there. There's the color there. This section right there that's made of this first 2 groups, that's going to be called S block. Okay, and then I got this middle section right there that's going to be between 3 to 12 here, and I'll tell you what those 3 to 12 are in a bit. That's going to be called the D block. Okay, and then I have this 13 to 18. Those are the P block elements. And then you have on the bottom here, this is going to be called your F block elements. Okay, well, in periodic table, the elements are arranged in terms of increasing atomic numbers. So I can look at the periodic table and you can see here the hydrogen being the very first element has an atomic number of 1. So this number you have on the top of the symbol is going to be the atomic number, which also represents the number of protons. So the helium is going to have 2. Lithium has 3, and so on. So all these elements are arranged in terms of the atomic number, or you can say in terms of the number of protons. Now, every single element in the periodic table is going to have its unique symbol. For example, hydrogen has a symbol of H. Usually, it's the very first letter that gives the symbol of an element. But obviously there is only 26 alphabets in English and we got more than 100 plus elements, so that means we may have to use another letter to identify some of the elements. So for example, in the second element is helium, which also starts with H, but H is already taken away by hydrogen, so you must have another letter with it. And the second letter in element symbols is always going to be the lowercase. The first letter is always uppercase. The second letter is always going to be the lowercase. So in this case, E is the lowercase, and so on. But then obviously there are going to be elements their name and their symbol really doesn't match with one another. And if I take one example here, which is sodium, sodium has an atomic number of 11. The symbol is actually Na. It really doesn't make sense. It starts with S, but the symbol is Na. And then I can take another example, maybe down here. Let's talk about gold. You know, gold is very famous. Gold is 79, and it's got an atomic symbol of Au. Obviously, doesn't really start with A when we say the name gold. Then in those cases, a lot of time their symbol comes from the Greek letters. Like gold is called auric in Greek letter, and so that's where their symbol comes from. So you want to make sure you know the symbols of the elements up to 30. All right, you don't necessarily have to memorize those, but make sure you know the symbols of these elements up to 30 for most of the cases. And you also want to make sure you know some of these common elements like gold, you got silver, okay, we got this mercury. Mercury is also very famous, and we got tungsten. Some of these common elements that have been used a lot, or they are very famous just because what they do in real life. In a very typical periodic table that's going to be given in any exam will be containing the symbols, will have the atomic numbers, and they will have another number right underneath the symbols, and that's going to be the atomic weight or the atomic mass. The atomic mass actually comes from the mass numbers, and I'll tell you in a little bit how the atomic mass is retrieved from the mass numbers. You'll be lucky if you're given a periodic table that has the names along with them, but for the most part, a typical periodic table that's given in the exam just have the symbols, the atomic numbers, and the atomic masses. Okay, well, moving along, the periodic table has gonna have the metals and the nonmetals, and to separate the metals and the nonmetals from one another, we can look at this zigzag line that's right there. So make sure you focus on where that zigzag line is. This right there. And there is a good chance the periodic table that you guys are going to be given in the exam may not necessarily have that zigzag line as prominent as we have in this case, but make sure you just know the location of this zigzag line. Okay, so anything onto the right side of this are going to be the nonmetals. So these guys are going to be the nonmetals. And anything that's onto the left side are going to be the metals. I'll write down the metals on right here. Okay. Anything that sits right on the top of the stairs or the zigzag line. So we got this boron, we have this silicon, germanium, arsenic, antimony, and tellurium. These are actually going to be your metalloids. All right, so I'll just write that down here. Those are your metalloids, or also called semi-metals. So they have the properties of both the metals and the nonmetals. How about that? Okay, so then we have about 18 groups in the periodic table, or 18 vertical columns, as you can see, going from 1 all the way to the 18 in the periodic table. So that's 1, and this is down here is going to be 18. So those vertical columns are actually going to be called groups. Okay, so there's two ways of numbering the groups. You can number the groups from 1 to 18, or you can number using alphabets like 1A here, 2A here, and then we skip the D block, and then we have 3A, 4A, all the way to the 8A. Now, numbering the elements this way is more important or more beneficial than numbering these groups from 1 to 18. Okay, well, we'll talk about that, how they are more useful in a little bit. Then in addition to that, we have about 7 horizontal rows in the periodic table. So we got 1, 2, 3, 4, 5, 6, and 7. We got 7 horizontal rows in there, and they are actually going to be called periods. And they do represent the shells. And probably just go back. These group numbers actually represent the valence electrons. So remember I talked about the valence electrons in the outermost shell. You don't necessarily have to draw the structure every single time. You can figure out the valence electron by looking at the group number. Okay, so let's go back to that in a little bit. If I'm talking about, let's say, calcium, and the question is asked how many valence electron calcium has, you don't want to draw the structure of the calcium to figure out how many valence electrons it's going to have. Well, calcium is actually in group 2A, so that means it will have 2 valence electrons. Okay, well, let's take another example. What if I have chlorine down there? Chlorine, which is 17, it's in group 7A. So since this is in group 7A, it's going to have 7 valence electrons. So these alphabet group numbers actually gives you the number of valence electron in a particular element. So you don't want to draw those every single time. Make sure you know this. It's going to be very useful as we're going to be moving along. Now, a lot of these groups has some common names. So that, for example, this first group, or group 1A, is actually called alkali metals. All right, so group 1A, or I can just say 1, is called alkali metals. Okay, the group 2A, or just the group 2, are called alkaline earth metals. So the elements in alkali metals, we're going to have lithium. So I can probably just write that down here. So going from lithium, sodium, all the way to francium are going to be considered your alkali metals. Now keep in mind, hydrogen is your non-metal, is the only non-metal that's placed in the wrong spot. Not necessarily the wrong spot, but it's placed on the metal side, even though most of the non-metals are placed onto the right side of that zigzag line. So since this is a non-metal, you don't really consider it an alkali metal. So your alkali metal starts from the lithium all the way to the francium. Okay, then when you look at your alkaline earth metals, we can start with beryllium, that's in group 2A, and then we got magnesium all the way down to the radium. So those are going to be your alkaline earth metals. You don't really have any common names for groups from 3 to 12, or even group 3A or 13, 4A or 14, 5A or 15, or 6A or 16. Then you have this 7A, or group 17, so that I can say group 7A or group 17. They're called halogens, and the halogens we got in there are going to be the fluorine, chlorine, all the way down to the iodine. Okay, and then we got these noble gases, that's going to be group 8A or group 18. And that's going to be your helium, neon, and so on. Okay, so all the way down, those are your noble gases. The noble gases are actually the most stable element in the periodic table. Okay, when other elements do make the compounds, whether it's an ionic compound or covalent compound, for the most part, they try to become like noble gases by either losing electrons or gaining electrons, and then they go ahead and make compounds from there on. Okay, well, this is a very brief touch base of the periodic table. You want to make sure you know where the metals are, where the non-metals are. You want to make sure you can read the atomic numbers, the symbol, and the atomic masses. You want to make sure you know the sum of these common group names, and you must be able to read how many valence electrons we have in a particular element. Okay, well, let's move on and talk about how actually the ions are formed. If I have a neutral element, okay, so in a neutral element, what I have said earlier is the number of electrons is actually equal to the number of protons, because remember, the electrons are the one that carries the negative charge, the protons are the one that carries the positive charge, so they are actually electrically neutral. Now, as soon as they are not the same, that's when you're going to have an extra charge. Okay, now let's talk about how you make a cation and the anions. Well, cations are actually made from metals. So metals, they like to lose electrons, and when they lose electron, they get a positive charge on them, and I'll talk about how you actually get a positive charge once you lose electrons. On the other hand, if you have an anion, if you have a nonmetal, the nonmetals, they actually like to gain electrons. So they can actually do two things. They can either gain electrons or they can share electrons. All right. So we'll hold on to the thought of the sharing electrons for momentarily. They will make anions if they gain electrons. So when they gain electrons, they will have a negative charge on them. Okay, well, let's get back to the cation formation here, and let me take an example of maybe sodium. When I have sodium, and you can go back and look it up in the periodic table and see what the atomic number is going to be. Sodium has an 11 atomic number. So if it has an 11 atomic number, how many protons is it going to have? Well, it's going to have 11 protons. How many electrons is it going to have? Well, right now it's electrically neutral, so the number of protons must be the same as the number of electrons. So now sodium like to lose one electron. So let's say in this process, when it loses one electron, I'll tell you why I lose one electron in a minute, then how the distribution is going to look like. We still have 11 being the atomic number. We still have 11 protons, because remember, you never change the protons. If you change the proton, you're actually changing the elements. Once it loses one electron, so the number of electrons is going to be only 10. Okay. Now let's go back to this protons and electron number and focus on that a little bit. So we got 11 pluses there and 10 minuses there. So when I add this up together, it's going to have an overall of +1 left behind. So once sodium loses an electron, it's going to have a 1 plus charge on it. Okay. Well, why would I say the sodium actually loses one electron? So if I go back in the periodic table here, usually when we talk about the metals, however many number of valence electrons it's going to have, that's how many it's going to lose. Or another way of saying, all these metals or these nonmetals, they try to either lose or gain electrons so that they can get to your noble gases. Because remember, the noble gases are the most stable elements in the periodic table. So sodium being 11, okay, what's the closest noble gas on that? It's going to be actually neon. So it must lose one electron to fall back onto the neon, so that's why it loses one electron. Well, let me ask you this. How many electrons should barium lose? Well, the closest noble gas to the barium is going to be the xenon here, which is only 2 electrons behind, so it should lose 2 electrons. That's one way of looking at it. The easier way of looking at it, whichever group number it's going to be, that's how many electrons it's going to lose. So barium being in group 2A, it will lose 2 electrons and it will fall back to the xenon. We don't really focus too much on the D block because they don't necessarily have a fixed charge or fixed number of electrons they can be losing. Now let's talk about maybe oxygen. Well, oxygen is a nonmetal, and the nonmetal actually gains electrons. So now let me ask you this question: how many electrons should it gain to reach the closest noble gas? The closest noble gas to the oxygen is actually the neon. Okay, so the neon is 2 electrons away, so it must gain 2 electrons to get to the neon. So let me write that down on the bottom here. So when I have oxygen to begin with, the atomic number is 8. It's got 8 protons and it has 8 electrons as well. Now we said it's going to gain 2 electrons. So when it gains 2 electrons, the atomic number is still going to be 8. The number of protons still be 8, but now the number of electrons is 10. So when I look at this protons and electron distribution, we have 8 plus and 10 minus here. So this is overall going to be 2 minus. So the oxygen, when it makes the anion, it gets a 2 minus charge. Okay, so how do you know how many electrons a particular nonmetal will gain? Well, you go back to the position in the periodic table. What about nitrogen? Well, nitrogen is 3 electrons away to get to the closest noble gas, which is neon, so it will gain 3 electrons. What about, let's say, iodine right there? Iodine is only 1 electron away from the stable noble gas, which is the xenon, so it will gain only 1 electron. So another way of saying the metals in group 7A, they get 1 minus charge. The metals, the non-metals in group 7A rather, gets a 1 minus charge. The non-metals in group 6A gets 2 minus charge. The non-metals in group 5A will get a 3 minus charge. And then carbon, if it does make an ionic compound, or if it does want to gain electron, it could gain 4 electrons. All right, so these metalloids, they behave a little bit differently, so we're not going to be focusing on these metalloids here. Now, coming back to the metal side, the group 1A, they actually lose 1 electron, so it's going to be plus 1. And group 2A is going to be 2 plus after losing 2 electrons. And then this group 3A, where we have the aluminum, the gallium, and indium. Those are the 3 we really focus on. They have a fixed number that number of electrons they can lose. That's going to be 3, and they get a 3 plus charge after losing 3 electrons. Well, we didn't really talk about the hydrogen here. What would hydrogen do? Well, since hydrogen is a nonmetal, and if it does want to gain an electron, it will gain only 1 electron because it's only 1 electron away from the helium, so it'll have a 1 minus charge on it. Okay, so that's how you figure out how many electrons a particular element will gain or lose, and how it will figure out how the charge distribution is going to be after that. Okay, now a typical element symbol or a nuclear symbol looks like this. I have an element symbol, I got the atomic number, and I got the mass number on the top. So that's one way of writing it, or I can just write it like this. Okay, and in the second way, they didn't really write down the atomic number, so this Z obviously represents the atomic number. The X is going to be the element symbol. The X is going to be the element symbol, and then A is going to be the mass number. The second way of writing the nuclear symbol is where they have written down only the element symbol and the mass number. You could see where they did not write the atomic number, because you can actually go in the periodic table and figure out what the atomic number is going to be. Now, I'll talk about what isotopes are. And in an isotope, you have the same number of protons and the atomic number, okay? But they will have a different mass number and the number of neutrons, okay? So remember this formula where we had said the mass number is actually equal to the protons plus the neutrons. So if your mass number is changing, there's something else must be changing if you're keeping the protons to be the same. In nature, you don't necessarily have to have only one type of atom, where you could have only, like I can have a hydrogen, but then hydrogen would have 3 different isotopes, where it could have 1H1 or 1H2 or 1H3. Okay, so in this particular case, I can try to figure out how many protons, electrons, and the neutron it's going to have. So obviously this top number represents the mass number, and this is going to be the number of protons or the atomic number. So every single element here is going to have 1 as your number of protons, because that's the definition of the isotopes. They must have the same number of protons. And if it's electrically neutral, the number of electrons would be the same as well. There's no charge on any of those, so the number of electrons would be the same as well. However, how many neutrons we're going to have in there, and you can use that formula, A equals to N plus P. So A being the mass number, so I know the mass number, and I also know the number of protons, so I can figure out the number of neutrons there. So in the first case, I'll have 0 neutrons, and here I have 1 neutron, and here I have 2 neutrons. So that's how you figure out how many neutrons and protons and electrons you're going to have in a particular element. So anytime you have the same protons and atomic number and even electrons sometimes, but different mass numbers and neutrons, it's going to be called an isotope. When it comes to finding the atomic mass, so I'm not going to do the calculations, but I'll tell you how you actually get the atomic mass. The atomic mass is the relative average of all the isotopes, mass numbers. Okay, so since in this particular case, hydrogen has 3 isotopes where the mass numbers are 1, 2, and 3. So when I take the relative average of those 3, that will give you the atomic mass. So when we say the relative average, it's not just the mathematical average. You have to look at their relative abundance, which means this first isotope may be most abundant than the other two, and in case of hydrogen, it is actually most abundant than the other one. This first one is more than 99% abundant, and then the other two are less than 1% abundant in nature. Okay, so that's how you calculate the atomic mass by using the relative average of all the isotopes mass number. I'll have a different session where actually I show you how you calculate the mass numbers, the atomic masses of these. Okay, so before I go, I want to do this last example, and I'll try to figure out how many protons, neutrons, and all those things I have in there. Suppose I have this sulfur 2 minus, and I write that down to be 34 there. Okay, so obviously this 34 is going to be your mass number, and let's figure out what the atomic number of sulfur is going to be. So if you go back, the sulfur atomic number in the periodic table is going to be 16. All right, so it's right below the oxygen. That's going to be right there. So it's 16 to be the atomic number, so the number of protons would be 16 as well. Well, how many electrons are we going to have here? It's not electrically neutral, so the number of protons and electrons are not going to be the same. It has a 2 minus charge, which means it's in an anion. It's got an excessive electrons. How many excessive electrons? It's got a 2 minus charge, means it has 2 extra electrons in there than the proton. So the number of electrons will be 18. And we already know the mass number to be 34 here. And how many protons we'll have? Well, that's going to be A minus P. So 34 minus 16, so that's going to be 18 in there. Okay, so that's how you're going to be finding different subatomic particles in a given atom or an ion. I hope this video was helpful, and I'll have some more videos posted related to the atomic mass and how to do those calculations.